All right. Hi, everyone. So today we're going to go ahead and jump into Chapter 5. So we started off this class talking about descriptive and inferential statistics. So in Chapter 5, we're going to be talking about the last type of descriptive statistic, which is the Z-score. So that's what we're going to be talking about today. I'm going to go ahead and share my screen so we can walk through the slides. Okay. So here we go. We've got everything rocking and rolling. All right. So Chapter 5, Other Descriptive Statistics. So this is going to be my completed slides that you can follow with your slides that you have on Moodle. So a Z-score. The definition of a Z-score is it modifies an individual score to convey the score's relationship to the mean using the standard deviation of the fellow scores. So we see that the Z-score uses what we already know how to calculate, the standard deviation, as well as the mean, to convey how far an individual score is from the mean. And this has two very important purposes. So the Z-score transforms a raw score, which we usually denote with an X, into standardized scores so that we can tell exactly where that score is in the distribution. So whether it falls close to the mean or far away from the mean, we get to see where that individual score lies on the distribution. It also standardizes the score so that they can be compared to other scores on different distributions. So for example, we can have scores from our class this year compared to classes from stats classes a year ago. Even those are on two different distributions. If we convert those scores to Z-scores, we can then compare them because they are standardized. So these are two important functions of the Z-score. So it helps us see where the score lies on the given distribution, and it also helps us compare different scores coming from different distributions because they are standardized. So that's that. Okay, so here's your formula for Z-score. So we take our individual score here, our X, we subtract it from the mean of that distribution, and then we divide it by the standard deviation. So this is how we find our Z-score. It's pretty simple. We already know how to find mean. We already know how to find standard deviation, so we're just taking those two bits of information that we do know how to learn, and we're combining them together to create our standardized Z-scores. So for example, if we have a raw score of 67, that would go here. If we have a mean of 73, that goes here. And then we put it over our standard deviation of 9. When you do that math, you get a negative 0.67. So here is how we would work out a problem for a Z-score. Pretty simple. We just take our raw score minus our mean over our standard deviation. So again, here's that formula here. You can do that with population data as well as sample data. So this formula here is the Z-score for population data as opposed to the previous slide. So if we go back a slide, here, this is for sample data. See here we have our X bar and our S, which denote sample sample statistics. But if we go to the next slide here, this is for population. So we see that the formula for Z-score is the same regardless of whether we are working with a sample or population. You do the same thing. So now on to the next slide. The Z-score is referred to as a standard score, as I said earlier, because it is the deviation score expressed in standard deviation units. So it tells us how far each individual score deviates from the mean, how far away it is from the middle of the distribution. So that's really important to note. The sign of the Z-score, so whether it's positive or negative, tells whether or not it falls below or above the mean. So if you've got a Z-score with a positive sign, that tells you that that Z-score falls above the mean, above the half of the distribution. If you've got a negative Z-score, it falls below the mean, so it falls on the left side of the distribution. So if we were to draw that out, let me see if I can do that on here. Draw. So excuse me, this may look just completely ugly. Okay. Okay, so there's our bell curve. Here's our mean, so that's in the center. If you've got a positive z-score, so a positive z-score, it's going to fall above the mean, so it's going to fall somewhere over here. If you've got a negative z-score, it's going to fall to the left of the it's going to fall to the left of the distribution. So the sign of the z-score is very important. The number of the z-score, so the number that you get when you do your formula, tells the distance, how far it is from the mean. So it tells the distance between the score and the mean in terms of standard deviation units. So I guess I should probably say, I don't know if I said earlier explicitly, that the mean of the distribution is always a 0 in a z distribution. So this is always going to be 0. Let me write that here. So this is always going to be 0. Your mean is always 0 when we have a standardized z distribution. So if you've got a score above the mean, it's going to be positive. If you've got a score below the mean, it's going to be negative. How big that number is tells us how far away from the middle or how far away from the mean that z-score is. So we've got two pieces of information to look for in z-scores. We have the sign, which tells us whether it falls above the mean or below the mean, and we have the number, and the number tells us how far away from the mean it is. If we have a big number, that means it's going to be farther away from the mean. If we have a small number, that means it's closer to the mean or closer to the center of the distribution. So if we've got a z-score of negative 3.30, that's going to fall to the left of the distribution. And it's going to be pretty far away. It's going to be like right here-ish. So because it's negative, it's going to fall to the left. Because it is a 3, that's kind of far out, so that's 3.3 standard deviation units from the mean. So it's going to be somewhere in this vicinity. Okay, we don't want to draw anymore. How do we get this off? Okay. Okay, I think I figured out how to get our drawings away. So we're good now. Moving on to the next slide. All right, so here is our z distribution, our standardized distribution. As you can see here, our mean is 0. So our mean is always going to be 0 with the z distribution. And we move from the mean in standard deviation units. So here we've got 1 standard deviation unit away from the mean on the positive side. Here we've got 2 standard deviations away from the mean on the positive side, and so on. And the same thing happens over here with our negative side. So these scores over here are below the mean, these scores over here are above the mean. We can also work the z distribution, or the z formula rather, backwards to find raw scores. So we can take that same formula, use algebra to move our terms around to find x rather than z. And this is how you do that using this formula here. So in order to find x, we would have our z, we would multiply that by our standard deviation, which is right here, and then we would add our sample mean. So for example, say we wanted to find x when we've got a z-score of negative 0.67, a standard deviation of 9, and a mean of 73, you would just plug and chug, and you would find your x doing it that way. So when talking about our z distribution, we have most of our scores falling in the middle. However, we also have scores that are falling out on the extremes. And if they fall far enough on the extremes, these are called outliers. So an outlier is an extreme score separated from others by at least 1.5 times the interquartile range beyond the 25th or 75th percentile. Basically what that's saying is that, let me get my little drawing thing going here. Basically what that's saying, and again, excuse me for my lack of skill. So we've got our mean in the middle, 0. Over here we've got this line, and this is going to be so this line here is going to denote our 75th percentile. And then over here, this line is going to denote our 25th percentile. Ooh, 25th percentile. So outliers are those scores that move 1.5 standard deviations past both the 75th and the 25th percentile marks. So those scores are the ones that are so extreme that they fall, let's change our color here. They fall somewhere over here. They're so far extreme that they are on the complete ends of the spectrum, the complete ends of the distribution there. So those are called outliers. So if you have an outlier in your data set, there are a lot of different things that you can do. First, you want to make sure that you have entered your data correctly, that it's not a recording error. Because sometimes that will happen. Say that you are entering data into your computer and you meant to enter just a 6, but you'll enter a 66 instead. And that can be an extreme outlier when it's in fact just an error and not a real data point. So first we want to make sure that it's not a recording error. Second, we want to make sure that we are sampling correctly. We want to make sure that we are utilizing random sampling when we can. So basically we want to make sure that everybody in our population has an equal chance of being sampled for our study. So we want to make sure that there's nothing crazy going on with our sample, that we have some anomalies occurring in our sample. So when you do get outliers, however, because they do happen sometimes, there are a lot of different things you can do. The most common thing you can do is run your analysis with those outliers included first, and then take those outliers out and run your analysis again and see if you get different results, and compare them. So see if you get different results from the first time that you ran it. That's usually a pretty common thing to do. If you do get different results, then you have justification to remove those outliers. However, if you have the same results, you have justification to keep them in. That's usually the way most researchers handle outliers in research. So that's outliers. Let's see, let's clear this. Clear all drawings. There we go. There's Mark. He's giving us a little message there. So box plots. This is an important graph that we didn't talk about in Chapter 2. That is a really good way to graphically represent our data, because unlike some of the other graphs that we talked about in Chapter 2, the box plot helps us see what the form of our distribution is. It helps us see whether or not it's normally distributed or skewed, something like that. So the box plot is a graph that shows a distribution's range, interquartile range, whether it's skewed, And it also tells us things like median and other statistics like mean and outliers and that sort of thing. So this is what it looks like. We've got our box here, and then we have our whiskers here on the end, these little lines here. So sometimes this is also called a box plot, a box and whisker plot. So that's another name for it. So the top whisker here denotes our upper extreme, so that's the highest score in the data set. The lower whisker here is the lower extreme, so those tend to be our lowest scores. You can also denote outliers with a little dot like this here. This line here represents our upper quartile, and that's also called our 75th percentile. So that's this one here. The lower quartile, also called our 25th percentile, is the other edge of the box. So that's this one here. And then in the middle, we denote a line with our median, because remember, that's our midpoint. So that's all the parts of our box plot. Make sure to understand all of these parts because you'll have to identify them for your test. So make sure you understand all of them. Here's some other examples of box plots. You can have them vertical like the previous slide, or you can have them horizontal like in this slide. So here we see a pretty skewed distribution happening here. We've got our median, we've got our 25th percentile, we've got our 75th percentile, and we have our whiskers showing us our extremes. We also have an outlier happening here. This one's a little bit better with our distribution, but still a little skewed. We've got our median, 25th percentile, 75th percentile, and our highest and lowest values. So make sure that we understand all of these parts and that we can identify them for the test. So interpreting box plots, this is pretty much going to reiterate what I just said. The inside line in the box is the median, the dot is the mean. Oh, so that's something I didn't cover earlier. Let's go back a slide. So some box plots have dots inside of them like this one here. And we use those dots to denote where the mean is. So you can see here that we've got a bit of a skewed distribution, a little bit better than this one, but still skewed because our mean and our median are not falling on the same number. So our mean within the box denotes the mean. Or I'm sorry, the dot within the box represents our mean. The line within the box represents our median. So next slide. So the dot in the box is the mean. The box covers our 25th to 75th percentile ranges. The whiskers denote the extremes of the box plot. In the skew is the relationship of the mean and the median that we see in the box plot. So you can tell whether or not your distribution is normally distributed. And that is it. So that is chapter 5. And again, if you have any questions on the stuff that we covered, feel free to email, and I will get back to you as soon as I can. Have a good day.